Every time you snap a picture with your phone, you're basically hiring quantum physics as your personal photographer. Light enters the lens in tiny packets of energy called photons. When they hit the sensor, they transfer energy to electrons in the silicon, and your phone turns all that activity into numbers, colors, and eventually an image. In other words, your camera doesn't see an entire landscape at once. It gets hit by a shower of tiny light particles and keeps track of what happened across every little section of the sensor. This strange behavior of light is part of what Einstein helped explain. The more photons that arrive, the more information the sensor has to work with. That's why photos taken in the dark often look grainy. The camera is trying to rebuild an entire scene from a limited supply of light. Today, the same idea that changed physics is used to photograph sunsets, suspiciously photogenic meals, and 20 nearly identical group pictures because somebody blinked in the first 19. Stimulated emission. If you've ever scanned groceries at a checkout, watched something on a disc, or used fiber optic internet, your day has depended on some extremely well organized photons. Inside a laser, particles absorb energy and become ready to release light. When a photon with just the right amount of energy passes by, it can trigger the release of another nearly identical photon, traveling in the same direction and moving in sync with the first. The process repeats until it creates a narrow, precise beam that's far more disciplined than the light from an ordinary bulb. Instead of every photon heading off in a random direction, most of them move together like a suspiciously well-rehearsed parade. That beam can scan barcodes in a fraction of a second, perform delicate surgery, and send information through cables stretching across entire oceans. The internet may feel invisible, but a huge part of it is just light racing through glass, desperately trying to load your video before you lose patience and click on something else. Energy transitions in LEDs. The LED bulb above your head doesn't have to heat a wire until it glows. It produces light in a much more elegant way, by making electrons lose a very specific amount of energy. Inside the material, electrons aren't allowed to have just any amount of energy they feel like. They can only occupy certain levels. Think of it as an invisible staircase. An electron can stand on one step or another, but it can't stop halfway between them and take a break. When an electron drops to a lower level, the leftover energy can be released as a photon, and the size of that drop determines the color. A larger drop can produce light closer to blue, while a smaller one can push the color toward red. That's how lamps, signs, and screens create color without painting every individual pixel. By mixing tiny red, green, and blue lights at different intensities, a screen tricks your eyes into seeing millions of different shades. The image in front of you is really a crowd of electrons dropping down microscopic steps at exactly the right time. You see a TV show. Behind it, billions of tiny energy drops are happening with more coordination than most teams can manage on a Monday morning. Quantum tunneling. Imagine throwing a ball at a concrete wall. It hits the wall and bounces back. That's reality behaving itself. But electrons don't always respect that kind of common sense. In the quantum world, a particle can sometimes be found on the other side of a barrier, even when it doesn't have enough energy to get over it. It doesn't punch a hole through the wall, climb over it, or fill out the necessary paperwork. There's simply a chance that it will appear beyond the obstacle. That phenomenon is called quantum tunneling. The memory inside your phone, flash drive, and solid-state drive uses this effect to store information. An electric field pushes electrons through an incredibly thin insulating layer and traps them inside a tiny part of the device. Whether that electrical charge is present or absent becomes digital information. Your photos, messages, and files remain saved, because certain electrons were placed on the other side of a microscopic wall. The trick doesn't last forever. After enough writing and rewriting, the insulating layer slowly wears down, and some electrons can begin to escape. Even digital memory gets old. It just does it without complaining about its lower back. And no, this doesn't mean you should try walking through your living room wall. The larger an object becomes, the more ridiculously unlikely tunneling gets. The universe offers a cheat code, but only to things small enough to fit on the subatomic scale. Atomic transitions in GPS clocks.